This is section 1.4 in your textbook. We're sketching graphs of functions. We're given 6 graphs at the beginning of this section. It's rather confusing when you get functions written in this function notation here. You see 2f and then 0.5 bracket 0.5 bracket x minus 1 bracket close bracket plus 3. What this means here, when you have this, is it's applying all these transformations to this function, which is the parent function. Okay? So to get from this equation here to this graph, you actually have to sub in this x squared. Okay? And the way you do this, it's kind of a reverse sub. And what I mean by that is whatever you have in brackets here, goes in for x in the parent function. Okay? So the actual equation then for this graph in red wouldn't be this 2f.5 x minus 1 plus 3. It would be this. So y is equal to 2. Now you're going to sub in everything in brackets for x. So you put in a big brackets here, 0.5 x minus 1 close bracket all squared plus 3. Okay, so this is the equation for the graph in red. Okay, and that might be relatively easy for you guys, and you just see that makes sense. But when we get to more complex equations like this, 1 over x, can get a little trickier. So this equation for this graph in red now is going to be y equals 2. It's a reverse sub, so you're subbing in everything in brackets here for x. So we can put 1 over Any questions about that? See how complex it can get? And when you have now a sine function, it gets even uglier, right? So this red function here, the equation is not this, but you're going to take whatever's in brackets and sub it in for that x in the sine value. So sine, everything in brackets here. Okay, is that clear? Just going from function notation here to the parent function graph, people will mess up. Okay, students will mess that up. And then you don't have any chance to answer the question correctly. Any questions on how to do that? Just to go from here to here. Anybody not understand that? Yeah, Alex.
So like everything that's in the brackets, you sub into
to the green or the parent function, yes.
Okay.
Yeah, where x is. Okay, so notice I left that 1 on top by itself. And then where x was, I subbed in everything in brackets. Okay. Not this plus 3. I still left that on the outside. I didn't put the plus 3 down here in the denominator. Okay? There's numerous ways to mess this up. Okay, that's one of them. If you sub in everything for x, you're just subbing in what's in the brackets for x. Okay, I left that 2 on the outside and I left the 3 on the outside. Okay? Once you sub in for x, you can actually apply BEDMAS and make this equation a little easier on yourself. Okay, we know 2 divided by 0.5 is 4. So this is actually 4 over x minus 1 plus 3. Okay? You can do some math there and cancel those out. So now we know that this graph in red is actually just a vertical stretch of 4 with the critical point moving 1 over to the right and 3 up. It's a vertical stretch of 4. So I combined the vertical stretch of 2 and the horizontal compression of 2, or 1 over a half, right, which is 2, into a vertical stretch of 4. Okay?
So is there still a horizontal stretch or no?
For this one, no, because there's no longer a k value here in front of x. Okay? So for instance, for this one, you could make this one easier by saying this is 2.
Zero times.
Okay, so I'm applying this square both to the half and to the x plus 1. So squared, 1/2 squared is 1/4, so this is 2 times 1/4 times x minus 1 squared plus 3. 2 1/4 is just 1/2. Okay, so this vertical stretch of 2 and a horizontal compression of 2 becomes just a vertical stretch of 1/2. Okay, so depending on the parent function, this vertical stretch and this horizontal stretch react differently, okay, with how they're combined, depending on the parent function. That's why in certain graphs we're going to see a stretch, in certain graphs we're going to see a compression once these transformations are made. Any questions about this, the math I've done here?
So for which graph is that?
This is for this graph right here. Okay? When in doubt, if you have any doubt about what the graph looks like or what the transform graph should look like, always take a value and plug it in for x. Okay? And see if you're getting that y value. Okay? Or even create a table of values and make your plot that way if you're not totally comfortable with your transformations and you want to verify them. Okay? Any questions about how it's subbed in for x, going from this formula to this formula, or simplifying the formula? Joseph.
So why did it end off at 1/2 again?
2 divided by 4.
Is that a 1/4?
Yeah, this is 1/4. So 1/2 squared is 1/4.
Oh, okay.
Yeah. Okay? Just like this, right? 1/2 squared is 1 squared over 2 squared, which is 1/4.
So you square the value before you go to this one.
Yes. Yeah.
So
Yep.
the 2 before the f means the whole equation is doubled? For all of them?
This 2
Yeah.
means there's a vertical stretch of 2.
No, I understand that being on, it says 2f, 2f,
Here?
for all the red equations, yeah.
Yeah.
That means it's doubled?
No, it means there's a vertical stretch of 2 to this parent function. Don't think of it as doubled. No, there's a vertical stretch of 2, okay? But then if you sub in this value into the parent function, you can actually cancel the vertical stretch and the horizontal stretch to make one value, okay? Through BEDMAS. Yeah, Jason.
So whatever's in the brackets and the function, you transfer it to the parent function?
Yes, whatever's in brackets here, which is, all of these are the same, right? It's 0.5 x minus 1. That goes in for the x value here. Okay? So it's very strange. It's kind of like a reverse substitution. You're substituting the parent function into this function, but you're actually substituting what's in brackets into the parent function, but maintaining this equation, so everything else, the 3 and the 2. Okay, so a lot of people get confused there. Yeah, Lyndon.
So for the one on the left, I mean on the right, the last one, yeah.
Yeah.
How you got 4 over x minus 1? Is it since 0.5, 1/5 is 0.5 equals 2? So would you multiply the 2 outside on the inside? Are you basically foiling it?
No, I'm not foiling anything. It's just 2 divided by 0.5 is 4. Okay, this is the same as 2 over 0.5 x minus 1, right? So 2 divided by 0.5 is 4. Okay? How many times does half go into 2? 4. Any other questions with this? That's really important. We kind of skip over that because it's assumed that you remember that or know that from grade 11, but a lot of people get lost and confused there. Any other questions with this before we move on?
How do you do absolute x?
Sorry?
Absolute x. Why x?
Absolute x? Okay, sure. So this one, you're just going to take, so we're doing this graph now. Y is equal to 2. Now, I'm going to take everything that's in brackets and substitute it in for x.
how would you make that simpler, I guess?
So 2 multiplied by 0.5 is 1. So this is going to be the same as this.
It's not on the screen.
Thanks. Okay?
So can you move it over a little bit? Thanks. Why isn't plus 3 inside the absolute?
The plus 3 because it's not in the brackets of the original red function. Okay? Yeah, that is actually quite confusing, right? There's a lot of people that will make that mistake. Okay, so whatever's in brackets in that the translated function, you're going to substitute it in for x in the original function. So I take that and I substitute it in for x. And then you can make adjustments or combinations. All right, so it says the first one, identify the parent function of each graph. This is easy. Besides the fact that they tell us what it is in green, we should recognize it, right? This is x squared. This is 2, or an exponential function. Joseph?
So why do you only distribute the 2 to the 0.5 and not to the x minus 1?
Because everything's multiplied, right? So you can only multiply it by one of them, right? It's just like 2 times 3 times 5, right? You're only going to multiply to 1, right? Okay. Any other questions with this? So we should know all the parent functions. We should recognize them. All right, if you don't, make sure you study them, that big graph we did yesterday. All right, next page. Yeah.
For the first example, where'd you get the exponent of 2?
The exponent of 2 here?
Yeah.
It's from this parent function right here. It's right there,
that
okay?
confused me.
No problem. Okay, moving on. Next it says copy and complete the following table for each parent function. I'll put them over here again. Okay, we should know these from the big table we wrote out yesterday. It was also part of the homework. The domain for y equals x squared, we should know that's xer, right? The range is yer, where y has to be greater and equal to 0. Okay? These are all directly a straight review from yesterday. Okay? So I'm going to write in here yesterday table. This is the handout I gave you guys. Okay? Turning points is the only new one. So it describes here, defined by a turning point is here on the left. It's a point on a curve where the function changes from increasing to decreasing or vice versa. So here we see the point A is a turning point and point B is a turning point. So let's just go back to our parent functions now, which are in green. And I'm going to circle the turning point, okay? Or someone can tell me. Nicholas, what's the turning point for this one? No, right here. Yeah, where does it change direction, the graph? What coordinate point? You can see it on the screen. See my pen? See this? Yeah, so at what point does the green graph change directions?
0.
Yeah, 0 what?
0 and
Good, 0, 0. So there's your turning point, 0, 0. Okay, Amber, where's the turning point here?
1, 2.
1, 2 is here. Does it change directions there? Is anything changing? It's going up here and then it continues to go up. So in this one, I gave you a bit of a trick question, okay? There's no turning point. All right. Daniel, turning point here?
There's no turning point on those either.
Right, there's no turning point. Why? Because the graph's always decreasing. Okay, if you look at the green line decreasing here, you look at the green line decreasing here. Okay? Turning point here, Joseph? Yeah, so is there a turning point? No, no turning point. Okay? Turning point here, Luke. Yeah, 0, 0. For green, and for red, what would it be? Yeah, it's a 1. 1, 3. Okay? And finally, Alan, the turning point for the green graph?
Would be at negative 360 and negative 1.
Negative 360 and negative 1, right? That's one turning point, yeah.
And then negative 270 and
right.
positive 1.
Perfect. Yep. So you know them. They're all here. Okay?
So
Yeah.
for the turning point, can't we just like write down like sine for the
Can you write down sine for the
like,
turning point?
How would you represent that?
I'm going to show you right now. For the sine graph, okay, it's right here. Okay. So here's that graph. So again, all this is from yesterday. Okay? So if you have your graph from yesterday, you might want to just add this last column or this last row on the bottom. Yeah.
For the last one, we said the critical was 360, isn't it actually negative 450?
This one?
Yeah.
No, it's 360 right there.
Is that when it's passing the negative? Is that where it's passing the x-axis?
It's right where, no, not where it's passing the x-axis. That's the zeros. We're talking about turning points. So where does it change direction? Okay, Lyndon? It's going down here. Now it's going up. So it's 360.
Yeah, but wouldn't you say it's change direction once it starts on that path, not halfway through it?
No, because it turns right at 360. It's going down, hits the bottom, then goes up.
That's not 360, that's right.
No, looks like 360 to me.
No, I haven't zoomed in, it's right here.
Oh, you're
Yeah,
right.
it's not.
Yeah, you're right. Thank you. So it would be what?
Or, no, it's,
It would be-
it's 90, 90 degrees.
450. Yeah, thank you. 450. I think that's kind of what Alan meant, though, right? You just misread the graph. Yeah. Thanks, Lyndon. Very good observation. All right. So here's that graph. There's the turning points. Let me explain a little bit how this works, because I'm not sure if you guys were confused yesterday. Nobody really asked any questions about it. But let's talk about this, what this means. Okay? So I guess we'll reference the turning point, since that's what we're doing. So it says 90 degrees plus 180K. All right, so let's think about that. I'm going to put that graph up. Okay, so what it's saying here, that K, as we know, ER means all real numbers or elements of the real. Z represents, it's actually a German word, I think it's Zihi, which actually means integers. Okay, who can tell me what an integer is? Yeah.
Points on the graph.
Points on the graph. Better definition than that? Yeah. Good. Positive and negative whole numbers. Very good. So positive plus negative whole numbers. So that's what this is saying then. K here, so see how there's a K are all integers? It's saying that the turning points are at 90 plus 180 degrees K, where K is equal to all positive plus negative integers. Okay, so let's just use a couple examples here. We'll use -2, -1, 0, 1, 2, 3. Okay, so if we sub in these values for K into this equation, we should get a turning point. All right, so let's see. 90 plus 180 times -2. Sorry?
It's not on the screen.
Oh, sorry. So 90 minus 360 is what? 270?
Negative 270.
Negative 270. So at negative 270, we should have a turning point. Let's see. So this is on the screen, yeah. So here's negative 270. There's our turning point. Okay? So now if we sub in -1, 90 plus 180 times -1, we should have a turning point at -90. -90, there's our second turning point. Okay? We sub in 0, 90 plus 180 times 0, we have 90 degrees, we should have a turning point at 90. And there it is. Okay? And the same thing goes for the intervals of increase and decrease. Okay, the formula is a little more complicated, 4K minus 1, but again, you're just subbing in 0, 1, 2, -1, -2 for K here. Okay? So we'll do one of those. Let's see. So it's saying that this is the interval of increase. 90, 4k minus 1, 2, 90, 4k plus 1. So let's sub in 0 for k. So we're going to have 90 times 0 minus 1, 2, 90 times 0 plus 1. So they're saying that this is an interval of increase. So from negative 90 to positive 90. So let's see, interval of increase from negative 90, yes, to positive 90 right here. Okay? Any questions about that? So here, this is our interval of increase. It's saying from negative 90, which is this point, up to 90, which is this point.
Which are also the turning points, right?
They're also turning points, yeah. Not sure if I mentioned this yesterday, it's in the book or not, but a closed bracket, this is equivalent, is saying that it includes that. Okay, let me explain that, sorry. If I say x is less than 3, but it's greater than negative 4, okay? Writing this in interval notation, I would write from negative 4 to 3, okay? So this is interval notation. Remember, this is not a coordinate point, x, y. This is an x and this is an x. If I write negative 4 is less than and equal to x, which is less than and equal to 3, then I use square brackets. Okay? So square bracket means including, or it's equal to as well. Open brackets means it's not including. Okay, so if I wanted to write something like this, sorry, last example, x is greater than 2, but less than and equal to 10. In interval notation, it would be like this. Okay? Make sense? So the 10 gets the square bracket. Because it's equal, yes. The 2 does not, because it's not equal. Any questions? All right, let's move on. Okay, so we've covered turning point. We've covered this table. C, identify the transformations in the correct order that were performed on each parent function to arrive at the transform function. All right, so we got to go back to this graph. Who thinks they can do this? So we're looking, they're all the same transformations. So we're looking at this graph here. Who thinks they can identify the transformations? Yeah, Jesse, go ahead.
So number 2 is the A value, so using vertical stretch.
Right?
0.5 is the K value, so it's a compression of half.
Yes, good.
Then the x minus 1 means a horizontal shift to the right, so positive 1.
Good.
And the plus 3 means it moves up 3.
Okay, good. And did you do it in the right order, Joseph?
0.5 is stretch or compression.
Sorry? It's a 0.5 is a horizontal stretch of 2.
Stretch.
Yeah. Sorry, did he say compression?
He said compression of a half.
Okay, my mistake. Yeah.
It's negative.
Yeah, isn't it technically the same thing? A compression of half and
Sorry, it's considered, my mistake, it's considered a stretch of 2. Okay? Because it's 1 over 0.5. Yeah, so whatever the value is of k, 0.5, you take 1 over that value, which is 2. Okay? So there's a stretch, horizontal stretch of 2. Okay, and what about the order? Did he say it in the right order? Yeah, okay, you want to kind of follow bed mass and do these operations before you do that vertical translation. All right, letter D. State the transformations that affected each of the following characteristics for each of the parent functions in the table above. All right, so let's look at that. Okay. Just going to go through each one step by step here. It's going to take a while, so I have the answers written here. For f at x equals x squared, and f at x equals the absolute value of x. The horizontal translation affects the turning point and the interval of increase and decrease. So we're looking now at this graph and this graph. Okay, that looks like it works. So it's saying what transformation, like what effects did the transformation have on domain? So we're saying that the horizontal transformation for this graph and this graph affected the turning point. Obviously, the turning point is not 0, 0 anymore. It's going to be over here. So it moved to the right. And same as this turning point moved to the right. And it affected where it starts to increase and decrease. Okay, it's pretty self-explanatory. Any questions about that part? For f at x, 1 over x, the horizontal translation affects the domain, the intervals of decrease, and the vertical asymptote. So this graph now, because we've moved it to the right, it's going to affect the domain. The domain being the only value that it couldn't be originally was 0. Now it's going to be 1. Right? Because it moved over 1 to the right. Okay, so that's how it affected the domain. It affected the intervals of increase and decrease because now you're decreasing up until 1, whereas previously you were decreasing up until 0. Okay? And the vertical asymptote again was moved from 0 to 1. The vertical translation affects the range and the horizontal asymptote. Again, the horizontal asymptote gets moved and the range now changes because the one value that it couldn't be was originally y equals 0. Now it's going to be y equals 3. Okay? This stuff is pretty easy. So for f at x squared, the vertical translation affects the range and the horizontal asymptote. I would argue that there's not a horizontal asymptote for y equals x squared. Okay, there isn't actually. This is incorrect. Okay, because we actually touch the value 0, so there's no horizontal asymptote. But it does affect the range. Okay, it's above 3 now instead of being above 0. Any questions? For f at x equals root x, which is this graph here, the horizontal translation affects the domain and the interval of increase. The domain now being from 1 and greater, not from 0. And the interval of increase, the same thing. The vertical translation affects the range, so now its value's above 3. Okay, pretty much all the same stuff here. For y equals sine x, the horizontal translation affects the intervals of increase and decrease. They all move now. All the intervals of increase and decrease are changing. It changes where the turning points are. Basically changes everything. Affects the range. Everything. Okay? Any questions about how the transformations are affecting this characteristics of the graph? I think that's pretty self-explanatory. E, what transformations to the graph of y equals f at x result in the graph of this? Hey, who can do this one? Sorry. Thanks, just keep letting me know because I'm looking down here. What transformations result in this graph? This is easy, right? There's even just a very simple parent function here. We're just saying y is equal to f at x, so there's no tricks here. What transformations are happening? Kevin in the middle.
So we have a reflection in the x-axis because the a is negative.
Good.
It's a vertical stretch for compressions.
Right? Good. So there's vertical compression because it's a half. Vertical compression. Yeah.
Translated up 2 units.
Yep. Sorry. Say that again.
To the left 2 units.
Right, because it's with the x, right?
And then down 1.
Good. All review. Any questions? All right, let's go to some of the example problems now. All right, example 1. State the function that would result from vertically compressing y equals f at x by a factor of a half and then translating the graph 5 units to the right. Very, very simple. We're just adding the vertical compression of a half and 5 units to the right. Remember the x value is the opposite sign. Okay? Any questions with example 1? Okay, example 2. Connecting transformations to characteristic of a function. Use transformations to help you describe the characteristics of the transformed function. All right. Yeah.
In a case like that, where it's y equals 3 times the square root of x to the minus 2, how do we tell if that's the k or the if it's affecting vertically or horizontally, like translation?
Because if it's horizontal, the k has to be with the x under the square root.
The square root's gonna stretch?
Would have to be like this.
Oh, okay.
Okay? The vertical it's on the outside, so this has to do with vertical.
No, for the translation, not like a stretch of compression. It's the same thing?
Same thing. The x would be in brackets, so it would be like x plus 3, like that.
Even if there's no vertical, it'll still be in brackets?
Yeah. Okay? All right, so it says use transformations to help you describe the characteristics of the transformed function. So here, what are the transformations that are happening here, David?
Which question?
The one we're on.
Oh, it's vertically stretched by a factor of 3 and it moves down to.
Good. So how can you relate that to the x and y values? Can you tell us? So if one of my x values was this, David, x, y, how am I going to change that based on this translation?
So your y value is multiplied by 3.
Okay. That's it?
And then just push it down to
Okay, how do I do that?
subtract 3
From y?
from, yeah,
Like that?
yeah.
Okay. And does anything happen to the x?
No.
No, good, because yeah, right, there's nothing happening to the x. There's no horizontal or vertical translations to it, and there's no stretch or compression. Okay, so another way of writing this, if you think of the general function like this, okay, everybody should be familiar with all these variables now. A, K, D, and C. D is in reference to the horizontal translation, K is in reference to the vertical translation, A is the vertical stretch or compression, and K is the horizontal stretch or compression. If you think of it like that, the general function, you can think of a transform function like this. Sorry, there we go. X over K plus D, AY plus C. So that's exactly what we did here. What I asked David to do without using a formula, he did. X over K, K in this case is 1, and D is 0, so we don't have to put anything in there. So we just put in X. AY plus C, A is 3, so we put in a 3 for A. And then C is negative 2. Okay? So important to know this formula. Very handy. If you can read out from a general function these values of these variables, then you can make those translations without having a table of values and figuring out each one. You can just use that formula. Okay, so very handy. I'll write it out again. K, X over K plus D, AY plus C. So this would be transformed point. Any questions? All right. Example 3. graph the function f at x equals cos x and the transform function y equals 2f at 3x. Where x is between 0 and 360, state the impact of the transformations on the domain, range, intervals of increase, decrease, and turning points of the transform function. All right, so you should all be able to graph this. F at x equals cos x, right? You should have this memorized. We used it enough in grade 11. Okay, only difference between this graph and the sine graph is we start at the top as opposed to in the middle for the sine graph. Okay, and now it's saying the transform function y equals 2. So there's a vertical stretch of 2 and there's a horizontal compression of 1/3. So this graph is going to move up and in. All right, so that's what we see here happening in red. So there's the graph I drew in blue, okay, a little bit more drawn out. Okay, and then we see that stretch of 2, so the amplitude, which was 1, becomes 2. And we see that compression of 1/3. So where we went through 1 loop originally, we're going to go through 3. 1, 2, 3. Okay? So going from here to here, you should be able to really do in your head. Right? You should be able to graph that really quickly in your head. Just like I graphed this, you should know that that 3 becomes a horizontal compression of 1/3, so this is going to go up and down 3 times. And that's it. Okay? Without getting so accurate, you should be able to go from here to here.